0 Kelvin, or minus 273.15 degrees Celsius, is the point at which no additional heat can be extracted from an object. For reasons we'll explore later, this temperature can never actually be achieved, but scientists have gotten impressively close. How close? About 1/1000th of a degree above absolute zero, a nanokelvin. Wow, that might be even too cold for us Canadians. To the best of our knowledge, the coldest temperatures ever achieved in the universe have been in labs right here on Earth. At such temperatures, a strange new state of matter arises that few of us are familiar with, a Bose-Einstein Condensate. This state of matter was first theorized by Albert Einstein in the 1920s. He used theories of quantum statistics put forward by Indian physicist Satyendra Bose to predict what would happen to matter at such cold temperatures. The results suggested that at very low temperatures, often on the nano or picokelvin scale, matter would behave very differently, in a way similar to how penguins deal with cold winters. Look at these happy little penguins from southern Chile. The temperature is warm enough that you can identify the positions and velocities of individual penguins in a 3D space. Now, if we go to the South Pole, the coldest place on Earth, the temperature drops down to minus 60 degrees Celsius. The birds huddle together so close that it becomes difficult to tell one penguin apart from another. They essentially become a single unit, a winter penguin condensate, if you like. Bose-Einstein condensates, or BECs, are very similar. When the critical temperature determined by this equation is achieved, the atoms in the system stop behaving like strong independent units of mass, and instead they condense into a single unit, the properties of which aren't defined by the Maxwell-Boltzmann distribution we're familiar with. Maxwell-Boltzmann distributions are used to describe the behavior of particles or atoms when the temperature is high enough or the particle density is low enough that quantum effects are negligible. For a slightly more complete picture of how particles interact, we must consult Enrico Fermi and Paul Dirac and use their quantum statistics model dubbed, unsurprisingly, Fermi-Dirac statistics. It turns out that a class of particles known as bosons stop following Fermi-Dirac statistics at sufficiently low temperatures. Instead, they follow Bose-Einstein statistics. Maxwell-Boltzmann, Fermi-Dirac, Bose-Einstein. At least now we have the answer to the age-old joke, how many physicists does it take to screw in a particle statistics model?